Yep. Camera on everyone. Let's start off. Yeah, so last class we have finished with capacitors. Today we'll be starting with current electricity. Like I keep saying, chapter is over capacitors. So in case you have not solved this before, finish it off by next Monday. Try to wrap up the chapter. At least finish, your booklet and maybe one more material. You're finding it tough, then at least finish your booklet and start doing, PYQs. So start working on that. Finish off, like every chapter you need to finish off at least one chapter per week. So that is there. So let's go ahead. Others, do keep your cams on. Current rate is again a pretty good topic, with a good weightage. It's like, think of like this. In mechanics, how is work per energy? That is like current electricity. In mechanics, rotational mechanics is like electromagnetic induction in electromagnetism. So it's a pretty good weightage topic. So let's start off. The starting is the definition of current, straightforward. Current, the symbol is I. It's simply rate of flow of charge. The direction of flow of positive charge is taken as the direction of current. So if you take a positive charge, and let's say if it is going this way, and if you take an electron and which is going this way, so the direction of the positive charge is taken as current. So we assume current is in this direction, but for an electron, current is going in the opposite direction. Unfortunately, we know in real life, the electrons are the ones which are responsible for charge transfer, but the way we define it is the flow of positive charge. So I is simply given by dq by dt. So from here we get the flow of charge delta Q is nothing but integral I dt, which is nothing but the area under current versus time graph. So if you draw a graph between current versus time, the area above the time axis is a positive area. The area below the time axis is a negative area. So positive area indicates charges gone in one direction, negative area indicates charges come back, right? And similarly, if you draw a QT graph, so in a QT graph, the slope will give you the current. And the average current is given by change in charge by time. That's it, straightforward definitions. So these are the main things here. I is dq by dt, delta Q is integral I dt, and I average is change in charge by time. And theoretically, remember this current, even though it has magnitude and direction, it is not a vector. This we studied in vectors ka starting mein. It's actually a tensor. We'll not get into that. What is a tensor and all. It does not obey vector laws. For example, see, if a current of 10 amperes flows from left and 10 amperes flows from right, how much current will come out from the wire? 20. But if it is a vector, it should have got 0, isn't it? So it has magnitude and direction, but it doesn't obey vector laws. Okay, have a look at this. So that's a bit about current. That's it. The straightforward definition, dq by dt. Let's see some problems on that. Any doubts on this? All clear with this? Going ahead, Adi, Arnav, Kush. Next thing, let's see a question. We have a charged particle plus q going in a circle with speed u and radius r. So the thing is, all these questions again will come in magnetism, because there we will study a current carrying loop will produce magnetic field. So charge going in a circle is actually like a current loop. Find I. So instead of a particle, what if you have a ring? You have a charged ring rotating with omega. Find current. This is a proton beam going with V, and inside it's full of protons. N is number of protons per unit volume. A is the area of cross section. Find current. Especially the C part ka result is important. Let's get them up. Right, Niharika. And remember, I taught you only one definition, I is dq by dt. Everyone should try. Right, Puraja. Get them. Get B and C. Finish it off. Devansh, try. Let's see. The first one is straightforward. I is equal to charge by time. So charge is q and the time is 2 pi r circumference by speed u. Qu by 2 pi r. In this, what you can do, there is a charge flowing at every instant, right? See, think of like this, Napuja. At every cross section, doesn't charge is crossing this area, isn't it? Charge is crossing continuously. So it's not zero. Charge is crossing through an area. So if you take a small angle d theta, if you take a small arc here, the dq on that small arc will be lambda into length, which is r d theta. Current I will be dq by dt, which is lambda r d theta by dt, which is lambda r omega. Or you could have done total charge lambda into 2 pi r by 2 pi by omega, isn't it? Lambda into 2 pi r will be total charge and 2 pi by omega will be time. You'll get lambda or omega. That also works. What about this guy? Take a thin cross section dx, area is A. So we get thin volume. So small volume will be A into dx. Then the number of protons in ADX will be n into ADX, the number of protons per unit volume into volume. Then the total charge Q will be number of protons, which is n into ADX into the charge of an electron, which is a proton ka thing. I is dq by dt, which is NEA dx by dt. I is equal to NEAV. Quite an important result. You should definitely remember this. We're going to use this in a derivation in today's class. So if you have a proton beam or something going on, the speed is current is NEAV. N is the number of particles per unit volume, A is the area of cross section, E is the charge, and V is the velocity. Check out these three. A and B we'll use in magnetism. C we're going to use it today only. You know how to make a better question out of the first one? They'll ask a question like this. We will see in modern physics, but the question would be of this sort. An electron is going in a hydrogen-like atom. So no question. An electron is going in a hydrogen-like atom in the nth orbit. Atomic number is Z. Then I is proportional to n power x and z power y. Find x and y. Question ऐसा आएगा. बताओ कितना होगा? Get it? An electron is going in the nth orbit of a hydrogen-like atom. Hydrogen-like atom. Atomic number Z. N is the principal quantum number. If the current is proportional to n power x and z power y, what is x and y? You will do this in modern physics later on, but I'm just asking one. There we will do a much better question. Do you guys remember atomic structure ka results? Radius is proportional to what? 0.53 angstroms n square by z. What is velocity proportional to? V is proportional to z by n. Do you guys remember atomic structure? Mein? We have to keep them and then solve it. So you need to know these proportionalities. If you don't know this, then you're gone. Getting it? How they got connected? Atomic structure ka results with current electricity. So anyways, so that would be means that is how the question will come. No one will ask you this question. This is easy. Clear? Next one. We have a hollow conducting shell. Here we have an ammeter which is grounded. Ammeter is a device which measures current. At a distance from the center, we have a particle here, charge plus q, which is going towards speed u, toward the center. This distance is d. Now see, whenever you ground something, what happens? The potential becomes zero. Due to whom? When you say potential of a shell is zero, due to which charges? Due to everyone present in the space, isn't it? Due to everyone. That means now when this charge is coming to make the potential zero, some charge will come from the earth, isn't it? So as it is getting closer and closer, more and more charge will flow. And if the charge is flowing, doesn't it mean there is a current in the ammeter then? Find the current at this instant. Gauss law and current electricity. Find current at this instant. So let's assume I is like this. Think how will you approach this? I'll give you 2 minutes. Right, Purva. Hmm. So let the distance be x. This is a kind of question, which is little difficult to figure out, but easy to solve. So let's assume there is a charge q induced on the shell. This is coming from the ground. Now, since this is grounded, the potential at the center must be zero. Now, the potential at the center is due to two charges. One due to the point charge kq by x, and due to the charge on the shell kq by capital R. This should be zero. Now I'm assuming a positive charge, but science will take care of it. So q is equal to minus qr by x. So as you're getting closer and closer, this is the charge induced as a function of x. And then we know current I is nothing but dq by dt. So when you differentiate this, you'll get minus qr, 1 by x ka differential is minus 1 by x square dx by dt. Now be careful here, dx by dt is not u, dx by dt is minus u, since x is decreasing. So if you substitute here, we get I is equal to current qr by x square with a minus sign minus u. The minus sign indicates, now see, we thought q was positive, but q was negative. That means charge was not coming onto the shell, charge is going away from the shell into the earth. You're getting it? So we have taken the direction wrong. The science will take care of it. So current, the negative indicates current is not flowing into the shell, current is going into the ground. There, we got the current as function of x. So put x is equal to d and we will get this thing. Can we take the potential on the speed? Yeah. Answer, there is no field inside God. In a hollow conducting shell, there is no field. The field is zero, potential is constant. It's an equipotential region. Clear? All clear with that? A hollow conducting shell, if there are no charges inside, it is equipotential, isn't it? Shielding effect. Charges will never enter inside. So this whole region inside is zero. This is equipotential. So if you can find the potential at the center, that will be the potential on the surface. All clear with this? Like I said, easy to solve, but yeah, you need to figure it out. Clear, Ahana? Pratik, Vignajit? Next one. We have three parallel plates. We have an ammeter connected between this and this. An ideal ammeter is like a wire only. It just measures current, but it does not create any potential difference. This guy ka charge is plus q, this guy ka charge is minus 2q, and this guy ka charge is 3q. We have done this. And this distance is d, and this distance is 2d. Then what happened? The central plate here started oscillating in SHM. X is equal to a sine omega t. The middle plate is oscillating in SHM. Now, again, what is the story there? If this plate goes here, won't the charge induced will change? If the charges will change, that means charge is flowing through the wire in and out. That means there is a current flow. Find the current in the ammeter as function of time t. Middle plate oscillates in SHM. X is equal to a sine omega t. Assume a is less than d. So you are not going to touch the other plate. Find current as function of time t. There, I just taught you one definition, I is dq by dt, but this is how the questions will come. SHM, Gauss law, current electricity. Anyway, I could have simply said you're going with uniform velocity also. It wouldn't have really mattered. Try, this is a good one. You got 2-3 minutes. Anyone not clear with the question, please ask me, I'll explain. Question is clear, go ahead, you got 2 minutes. How do we approach this? I hope you guys remember the result. Q1 D1 is equal to Q2 D2. Qa omega cos omega T3D. Okay. Could be the answer. I don't know the answer. So let's see. So when this plate moves this way, this distance becomes D minus X, 2D minus X. I'm assuming it is going to the right. Science will take care of it. This guy will be D plus X. What is the total charge outside? Remember, your Gauss law is still valid. What is the total charge on the outside plates? Total charge by 2. Remember? Total charges 2Q. So this will be Q and this will be Q. Let this charge be small q. Then this will be minus Q. If this is minus Q, then this guy will be Q minus 2Q. And this guy will be 2Q minus Q. And then we know Q1 D1, so this guy into this guy is equal to this guy into this guy. So from here we get Q minus 2Q into D plus X is equal to minus Q into 2D minus X. Bring all Q's to one side and this will be Q and that will be 3QD. So this will be Q into D plus X plus Q into 2D minus X. This will be 2Q into D plus X. The X and X goes off. We will get Q is equal to 2Q by 3 D plus X. Yeah, this is coming good. Now, what is the current here? Now, be careful. The current is flowing into this plate. That's what we assumed. So, I is d q plus small q by dt, the rate of change of this total charge. But luckily, capital Q is constant, so it ends up to be dq by dt. Yeah, done. So, differentiate this. This will be 2q by 3. D will go off, and then you end up with dx by dt. And we know x is a sine omega t. So just differentiate there and dump it there. So, that would be 2q a omega by 3 cos omega t. That's your current, everyone. Here are the steps. 90% is Gauss law. The only two things used is I is dq by dt. SHM though we just use the equation. As such, it didn't come anywhere. Any doubts on this? Please ask me. Since the current is going to this plate, the total charge on that plate cut differential must have been the current. And like I said, the science will take care of it. You just assume that is positive Q plus small q and let I flow from there. This is how you will get in advance. If at all advanced, this will be a moderate level question like. Clear with this? The main thing is people don't understand like, oh, how the hell if the plate is moving, how does the charge flow? Q1 D1 is Q2 D2. If you don't know that, you're gone. Because you know the result, it looks easy. If you don't know the result, this is really hard. You have to derive that. Clear with this? We have two parallel plates. Battery V, and we have an ammeter. Square plate side A. So we have a dielectric which is going with constant speed between the plates. And dielectric slab of length A, so the same length as the plates, enters a capacitor with a constant speed U. Plot current versus time graph. So at T0 it starts entering. Distance between the plates is T. So the slab is entering with constant speed and it leaves the plates with constant speed. So it is just going through. So during this process, again, get the story, get the context first of all before starting a problem. Why the hell are you getting current? That is a question you need to always ask. If the slab goes inside, what happens to the capacitance? Increases. If capacitance increases, what happens to the charge? Increases. That means you're getting a new charge on the thing. There's a charge continuously being pumped. And if the charge is flowing, it is called current. Get in the context. So you need to always ask your question, like when you say find the current, like boss, charge, why the hell the charge is coming? Without that, don't jump into a problem. Get the context. Why is the charge changing? And then you start. Try. I'll give 2-3 minutes. And this is not new. This you have done. You just don't realize it maybe. Try for a minute or two. Then I'll show you where you have done this. Where you have seen this? You have seen this in the last chapter. Isn't it the same question? Sorry, current. This one. Isn't this the same question? Just rotate this 90 degrees. If you rotate this 90 degrees, it is the same question. Karna kya hai? You have to find capacitance. You have done already last time capacitance. Once you know capacitance Q is equal to CV differentiated, you're done. So you can treat this as two capacitors. So let's say this thing has gone X inside. This is filled with a dielectric slab. So this capacitance C1 will be area, which is A into X, K epsilon, the medium has changed by distance D. This guy is still vacuum C2, which will be A minus X into X, A, epsilon by d. So we get C equivalent will be A epsilon by d into A plus x into k minus 1. Charge q is equal to C equivalent into V. So that would be A epsilon by d V A plus x into k minus 1. Current I is dq by dt. That would be A epsilon V by d into k minus 1 and dx by dt. Dx by dt is speed. And if you observe this, this is a constant value. But there is a catch. So the moment you see this and you ask the people to draw the graph, that's the reason I asked you to draw the graph. How does the graph look like? Think I'll give 20-30 seconds. Itna to right tha. There is nothing wrong till here. But the moment I ask a graph, there is something there. Trap is there. Look at how the slab enters. This is the scenario at T0. Somewhere in the middle, you're like this. You're completely inside at T is equal to A by U. So during this time, C equivalent increases. Therefore, Q increases. Therefore, current is coming out of the battery. So current is actually flowing like this. But once you cross this, the slab is going out, the capacitance is decreasing. So this will happen at 2A by U. C equivalent decreases. Q decreases. The current actually started flowing in the opposite direction. The sign has changed. This is not an SHM. Current goes into battery. Magnitude is still constant, huh? So if I ask you to plot the graph, I versus T, so current is initially positive till A by U, then it drops, it becomes negative, so it's still constant. Then at 2A by U, it becomes 0. So after 2A by, the slab is gone. So the graph looks like this. The thing is, when people see constant, no, they'll just draw a line like this. I think that is the answer. And that will be there in the option. You won't realize the current has changed sign. Is that clear, everyone? So charge was going into the capacitor and then coming back into the battery again. So current direction has changed. After A by U, the current flow will reverse. All clear with this? Yeah, this is a capacitor and current electricity. And again, we just did one definition dq by dt. This is how the kind of questions you can ask. Any doubts on this? You can even make it even better. You leave the slab there. Now this is going with constant speed, no? If you just leave the slab there, then there'll be a constant force, isn't it? Then F is equal to ma, that means the slab will accelerate. That means current won't be constant, isn't it? This slab will be doing a periodic motion inside and outside. Then current, I think, will come like something like t square function. So you will get something of, I'm not sure exactly how. I think maybe it will be something like this, parabolas types. You'll get a parabolic something like this. Graph will continue, it will be continuous. Matlab, it will never stop. It will just keep on oscillating. You can play like that also. Because the force is constant, the slab will be doing a periodic motion. But this time the speed is not constant. Na? V is equal to AT. So you'll get a linear function. I think the graphs will be like this. You'll get triangular functions. I think you'll get something of this sort. I'm not sure. You have to check it out. But yeah, that also you can do. That would be much better than this. Clear? Then this is just on a definition dq by dt. Next thing. Drift velocity. Now, if you take a conductor and if you just observe the electrons inside, you will see these electrons are just moving in random directions. Getting it? Basically due to collisions. Anyone remember where we have discussed something like this before? Which chapter? KTG, right? Yeah, random motion, Brownian motion, systematic motion. Temperature is a function of random thermal, random kinetic energy. So there it was gas molecules, here it is electrons. So electrons move in random directions. Due to collisions. We call this Brownian motion. Now, because they're going randomly, the displacement is zero, so the average velocity will be zero. That means for every one electron that goes to the right, there is one electron going to the left. So this will not create any current. Because there's no net charge flow. And the unfortunate thing is this, these things go pretty fast. If you actually try to find the kinetic energy, this is the thermal kinetic energy. So the reason the electrons move is because of the heat temperature. This would be 3/2 kT. K is the Boltzmann constant. This would be half into mass of electron into velocity square, which is thermal. If you calculate this value again depends on the temperature and other stuff, will be in the range of around 10 power 5 to 10 power 6 meters per second. Pretty fast. You're talking in the range of 100 to 1000 kilometers per second. And these things are going so fast, but they won't create any current because they're just randomly moving around. This is what happens. Someone has a super high IQ, super high IQ, very intelligent and all, but you don't focus on one thing. You do 10 different things at the same time. That's what happens. So there. So one thing is clear. So this is not going to create any current. Then who creates the current? So if you take the same conductor and try to put it in a battery, let the voltage be V and let the length be L. We know, we have seen electric field will be potential difference by length. This will create a field E here in the region. And because of this, the electrons here will start getting pulled this way, F, which is E into E. So these forces, now if you see the motion, so this force, right, is actually dragging the electrons. So if you see the combined motion, it would look something like this. You're getting what is happening. So there is a random motion and there is a systematic motion. So this thing contains, so the moment you put a battery, both the motions go together, random plus systematic. The green one is your thermal kinetic energy. So the green lines, if you just take all the green lines and add them up, they cancel out. But the one who is actually making you move is the battery. The systematic motion is because of the field due to battery. This is responsible for current. Clear with this? Do you guys remember this KTGM? I told you this story, like, how one of my friend explained me Brownian motion, Sabir. Yeah, I'll just brief it up again in case you forgot. When you take, this Ganapati ka procession, when the procession is going from one point to another point, if you look at the people surrounding the procession, what are these people doing? People are dancing, jumping, they're moving around. You don't know what that person is doing also. They are completely random, isn't it? There's a crowd of 1,000 people, all are dancing and jumping and howling. It's pretty random, right? And these people are going with very high speeds. But the moment the procession goes from here to here, that same crowd, which is random, will also move ahead. So here we can see, a random motion is moving systematically. The whole randomness is being, continuously being pushed forward. So no matter how fast these people move, the procession will never go, isn't it? End of the day, the speed of the person or the average velocity of the person is the speed of the procession only. If the procession goes 1 hour, may 1 kilometer, his average speed is also 1 kilometer only. No matter how fast he is actually running around. So something like that. So we have a systematic motion and a random motion, but the systematic one is the main guy who actually pushes through. Now, so if you take this conductor here and we got on this electron, we have a force F is equal to E into E. E is V by L. And we get acceleration is equal to E by M. We define something called a drift velocity. So V drift is given by acceleration into tau. So what is this tau? Anyone remembers what is tau? Relaxation time. Anyone remembers the formula? बहुत इंपॉर्टेंट था. टोल्ड यू मेंस में आता रहेगा वो. फ्री मीन पाथ, कोलिजन रेट, याद है? 1/√2 pi sigma square eta v mean. Sigma is diameter, eta v is number of molecules per unit volume. V mean is root over 8RT by pi m. So from here you can clearly see tau is proportional to 1 by root temperature. So if you increase the temperature, the molecules will move faster. That means the same distance they'll cover in a shorter time. So they'll collide more. The number of collisions will increase, meaning the time also between them will decrease. So this is the reason in a conductor, whenever you increase the temperature, the resistance increases. Because the molecules of collisions have increased, it messes up. So there, meaning in case you forgot, tau is also given by free mean path by, that is where we derived from. In case you forgot, please go revise this. There. So once we got V drift, then we know I is equal to NEAV drift. This we have done today in problem 1C. Check. Once we got the V drift, you can take it and substitute here. We get I is equal to NEA. V drift is A tau. A is nothing but EE by M tau. We get I is equal to NE square A tau by M into E. Any doubt so far? We are getting somewhere from here. So we get I is equal to n E square tau by m into field, which is n E square by tau by m v. There is an A also. V by L. Remember, V is your voltage. So we'll get V is equal to I into m by n E square tau L by A. This is what we call as V is equal to IR. Actually, we derived the Ohm's law. That whole constant there is your resistance. So where R is given by m into n E square tau L by A, we will simplify this into rho L by A. So this constant here is your resistivity. Which is given by the mass of the electrons by number of electrons per unit volume E square by tau. There, that's your main thing there. So V is equal to IR, R is equal to rho L by area. What is L? L is the length along the, again remember, you can't take any length that you want. L is the length along the current flow. A is the area perpendicular to the current. Rho is the resistivity, which is m by n E square tau. This is also written as 1 by sigma. Sigma is called conductivity. These are the main formulas, everyone. Now, from here, you can see a few things here. If you increase the temperature, I'll do one thing like it in the next page, but have a look at this. So if you have a graph like this, or if you have a graph like this, so here dV by di is your resistance R, but if your resistance also sometimes changes with current. So this is dV by di, this is called dynamic resistance. So you have a resistance which is changing with current. You do find such stuff. So here, so materials which obey Ohm's law are called ohmic conductors. So everyone doesn't obey V is equal to IR. This is a pretty good one. Matlab, you really can get hypothetical questions. Meaning they can ask like this, the error in calculating mass of an electron is 1%. The error in calculating charge of an electron is 0.5%. Find the error in calculating resistivity. Or they can say like this. In a hypothetical universe, the mass of electrons is double and the charge of electrons is tripled. What is the ratio of resistivity in the hypothetical material to the new material, old material? So if they ask something of that sort, if they start messing up mass of the electron, charge of the electron, then we are playing a different game. So then you need to know the derivation. Mains may generally they'll never do that. Advanced may you can expect. Clear with this? Next thing. These are important statements. Good theoretical questions. For conductors, with increase in temperature, the resistivity decreases. With increase in temperature, tau increases, tau decreases. Therefore, rho increases. And that implies resistance increases. So if you take a conductor and increase the temperature, resistance increases. For semiconductors, the story is a little different. With increase in temperature, agreed, collisions will increase, but you need to understand. Do you guys remember the difference between semiconductor and conductor? The free electrons, isn't it? In case of a conductor, you have a lot of free electrons. In semiconductor, you don't have enough free electrons. So when you increase the temperature, the number of free electrons will increase. You get more electrons to participate in conduction. So this actually dominates. Therefore, rho decreases. So if you increase the temperature, the distance decreases for semiconductors. But for conductors, it increases. It means if you take a copper wire and if you take a carbon filament, carbon is close to a semiconductor. So if you increase the temperature, carbon ka resistance will decrease and copper ka resistance will increase. Now, if you guys remember, there is in some other chapter, we had a statement like this. Listen to this. In some other chapter, we had a statement like this. If the temperature increases, some property increases for some materials. If the temperature increases, some property for some materials decreases. ऐसा कुछ statement था. Which chapter and what is that property? Anyone remembers? It's like this only. For one guy, it increases, one guy, it decreases when you increase temperature. By any chance, anyone remembers? These are good theoretical questions. They'll ask you these kind of things in bits or mains or some exam. Aditya. Right, Ahana. Two people got it. If you increase temperature, viscosity of liquids will decrease. But if you increase temperature, viscosity of gases, liquids will decrease, viscosity of gases will increase. याद आया? Don't forget this. So this and that conductors, they look kind of, not same, but they do. Clear this? And so the resistance R is given by R naught into 1 plus alpha delta T. So here R naught is the resistance at 0 degrees. Sometimes you'll get questions like this. The resistance of a so-and-so conductor is 100 ohms at 30 degrees. Find the resistance at 50 degrees. Then you use this formula. Alpha is coefficient of resistivity. This kind of looks like that linear expansion. Delta T is change in temperature. This L rate resistance as function of temperature. So this is the formula that is there in NCERT. So we'll stick to this. You should remember this. But there's a thing for large temperature changes. This is generally valid only for small temperature changes. that R kind of becomes like R naught into 1 plus alpha delta T plus beta delta T square. You start getting higher terms. We actually kind of ignored them for small temperature changes. So it won't be a linear function. But at an NCRT mains level, just stick to the linear function. And this alpha ka value, right? Alpha is positive for conductors because distance increases. Negative for semiconductors. That was a CD question. They said there are two materials, copper and carbon. What is alpha? So options were positive, 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 negative, negative, positive, negative, negative. ऐसा कुछ था. Easy question, but they do ask in CET. Clear with this? Next thing, current density. This is important, especially in magnetism. We're going to use this a lot. Symbol is J bar. So current density is simply current per unit perpendicular area. Let me put it in a better way. So even though current is behaves like a scalar, current density is a vector. If this is your current, J bar is the current density. This is your area. This is your area vector. There, this is the formula. So current I is given by J bar dot A bar, which is JA cos theta. This is the relation between current density and current. Direction of J bar is along I bar, current. And actually, if you see the formulas from here, we can derive this. If you say I by A from here, if you bring A down, this becomes J. So then we get a relation here. J is equal to sigma into E bar. Sigma is nothing but resistivity 1 by rho E bar. Quite a useful results again. This is the relation between the field in the conductor versus the current density. So that's totally how many formulas are there? You should remember them. The first one is this guy. I is NEA wave drift. You can note it down. We will need these formulas. We'll do some questions. I is NEA wave drift. This is the first thing you need to remember. V is equal to IR. R is rho L by A. It's okay if you don't remember this, but mains may generally they won't touch this, but advanced may they can. But this must you should know. V is equal to IR and R is equal to rho L by A. Then our resistance at temperature T is this guy. This one. This guy is really important. J is equal to sigma E1. Yeah, that's a bit of a theory about all this stuff. This is what we did right now, right? It's kind of little neglected one. When people say current, people are more focused on circuits, batteries, and all that. But there is a little thing like this also theoretically. All clear with this? Let's have a small break for 5 minutes. I can see people are getting exhausted. We'll have a small break, 5 minutes only. Come back. Go to washroom, wash your face, don't sleep. If you have to eat something, eat something. Come back in 5 minutes. Any doubts so far you can ask. Okay, come back in 5 minutes. Yeah, let's start off. So let's see some theoretical questions based on this. These questions will get things cleared. Let's get them. I'll give 2 minutes for 3 questions. Now better. Now people are looking a little lively. Let's get this. Right. Hmm. Let's say the first one. Wire of cross section, free electrons are moving through a wire. What is current in another wire? So we have I is equal to NEAV. Area is nothing but pi r square. So we can clearly see here, I is proportional to area, which is pi r square into velocity. So you're saying radius became half, so this guy is 1/4, and velocity became double, so this guy is 2, and C. B, so this thing I explained. So it's semiconductor decreases temperature, true. Conducting solid collision increases, true, but that's not the correct explanation. C. C is a good question. Let's see, will you fall into the trap? Yeah, some of you already started falling into the trap. Falling मतलब normal नहीं है, you went and jumped inside directly. Aditya तो अलग है. Trap is here. He went like this, then he came back and jumped inside. Vignajit got it. See, here it's an electrolyte, right? And there are solution there. So if you take cathode and anode, which is positive, right? Cathode or anode? Cathode is positive, right? No, anode is positive. Yeah, I get confused. So figure out whatever is positive. So if anode is positive, cathode is negative. Cathode, cation, so electrons. So chalo, let it be negative. So what will happen? So if you have electrons here, the electrons will go towards this way. And if whatever positive ions you have, they will go this way. But how does the current flow? The electron ka current will be this way, and the current will be this way. The currents will add up. Are you getting the catch? The particles will go in opposite directions, but the current will flow in the same direction. So current will be I1 plus I2. This will be N, E, A, velocity is V, plus this will be N, charge is 2E, A, and velocity is V by 4. 3 NE, A, V by 2. Is the answer. I think most of you subtracted it. That's why you're getting A option. That's it. So be careful. The particles will go in the opposite directions, but because of the charge, the current will be in the same direction. This was the starting definition. The direction of positive charge is given as current. Clear, everyone? All clear with this three? Let's do these two also. E is a good one. It was, yeah, first was easy. Current is constant, so I is equal to NEAV. So you get AV is constant. Kind of looks like equation of continuity, isn't it? Kind of makes sense also. In equation of continuity is what? Flow of liquid, right? Here it is the flow of charges. So technically there is no difference other than you're calling one is mass and one is charge. So if you have more area, you have less velocity. So P is greater than VQ. Get the E part. I'll give you a minute for that. That's a good one. Let's see. Right with Nachit. First one, see, the current at the cross section P equal to the current at cross section Q. True. Why? Same number of electrons will flow, like same charge flows per second. I don't care about the area. The question is how much charge is flowing per unit time. Same charge. The electric field at intensity P is less than Q. J is equal to sigma E bar. J is nothing but current by area. So E is proportional to 1 by A. So if you have more area, then you'll have less field. So B is also right. The rate of heat generated, yeah, no, this is good. We know heat is nothing but I square R. But we know current is constant. R is nothing but rho. Take a small cross section dx by area A. So we get heat per second when the current is constant is proportional to 1 by area. That means the thinner cross sections will have more resistance, therefore they generate more heat. And Q generates more heat. Yeah, that is right. The number of electrons crossing per unit area. Current is same, but if you divide current by area, the game changes. So yeah, D is also right. All four are right. Right, Niharika. All got this. It's a good one. Any doubts on this thing? Please ask. No. There's one more theoretical thing. Remember just now we had a discussion like, drift velocity is very, very less. I didn't write that, but if you actually look at the drift velocity here, the V drift is in the range of 0.1 to 1 centimeter per second. Drift velocity is like too less. Your thermal speed was around 10 power 6 meters per second. This thing is 1 centimeter per second. So the theoretical discussion is this. The question would be like this sort. So if the current is due to the drift velocity, right, which is very slow. So whenever you're switching on your tube light or fan or something, from the switch to your bulb, the distance will be around 2 to 3 meters. So logically speaking, if the electrons are going with 1 centimeter per second, shouldn't it take almost 3 to 4 minutes for the bulb to glow? Right. But then when you switch it on, we know the bulb glows immediately. Energy travels, not electrons. What are you talking? Right, Vihan. The NEA formula N changes, but V is constant. Which part, Ray? Purvaja, you are asking. A changes, but V is constant. No, current is not constant. A and V both will change, na? If you increase the area, velocity will decrease to keep the current constant. I is constant.
नहीं but इलेक्ट्रिक फील्ड भी कांस्टेंट है ना सो
कहाँ पे constant? किसने बोला? इलेक्ट्रिक फील्ड खुद एरिया से चेंज हो रहा है ना? Electrical energy travels through car electrons. वो तो obvious है ना रे. Someone has to carry the energy. That is electrons only. Question वो नहीं है. If it is 2 meters, if you're going with 1 centimeter per second, it takes 200 seconds to reach the bulb. But the bulb glows immediately. And Omar, we discussed about the battery. What does the battery do? Does it produce electrons? So where are the electrons then? Electrons are all around the wire. It's like a conveyor belt. So think about this. The moment you switch on the conveyor belt, the entire belt will start at the same time, isn't it? So the ones who are providing energy to the bulb is not the electron near the switch. It is the electron near the bulb only. So Aditya, the word you have to use is this. The moment you switch it on, you establish an electric field throughout the wire. That electric field is dragging everyone at the same time. Nah, energy just doesn't go on its own. Nah, energy is still given by electrons only. So the question would be of this sort. Since V drift is very small, the electrons will take time to go from switch to bulb. Then the question would be then why does the bulb glow immediately? So the reason is that the electrons which are making the bulb glow is not the electron at the switch. So think of it like a conveyor belt. So the moment you switch it on, you establish a field E throughout the wire. And because of this, the electrons will start going in the opposite direction. So the best way to visualize stuff is not like, electrons are being pushed out, but think of a conveyor belt. This will actually be a small delay. Electric field travels almost at a speed of light. So if the wire is really long, it takes time for the current to establish. Right? Like a conveyor belt. Clear? Great. Let's see another question. We have a solid cylinder. radius r. J is your current density, which is J naught into 1 minus small r by r. It's an easy one. R is between small r to 0. J is your current density, which is current per unit area. R is distance from axis. These kind of questions, right, will be quite useful in magnetism. For now, it's fine. J we won't use much here. So look at this. If R is 0, current is maximum at the center, and as you go outside, the current decreases. So on the surface, the current is 0. Find the current in the conductor. Find the total current in the cylinder. In real life, na, current actually goes the other way. Center it will be 0 and outside it will be more. That's how an AC current actually flows in real life. But yeah, let's get this just simple integration. Remember, what is J? Current per unit area, unit perpendicular area. How do you choose an element? Right, Vihan. Right, Niharika. One more answer. Anyone else? Vignajit, got it. We have 3 answers. C. So we choose a thin ring here. This will be R, thickness dr. So current di will be J into area, which is 2 pi r into dr. Therefore, the current I will be J naught 2 pi integral 1 minus r by r dr. Limits will go from 0 to r. This would be J naught pi r square by 3. Check it out, you'll get that integration from that. भाई ना गुरु जब वो 2 and 6 3 हो जाएगा. You got it. Easy? Got this? But like I said, this questions again we'll see in magnetism. There I'll ask you find the magnetic field inside. This would be a part of it then. Next one is a good one. Next one is a question, where it is tough but easy to solve. So we have a composite wire. Composite wire meaning it's a wire made of 2 different wires. Matlab you took a copper wire and a steel wire and you connected them. So left wire ka resistivity is ρ1 and ρ2. A composite wire carries current I. ρ1 and ρ2 are resistivities. So current is I. Now, something happens and charge accumulates on the surface. That's the first thing. You need to figure out why the hell there is a charge on the interface. And how much is that? think for a minute, why are you getting charged and what is it? And then let me tell you, it's a standard question. You must have seen this maybe before, but it's a good one. So whenever you connect two wires of different material and pass the current, that interface actually starts getting a charge. It is removed in the portion now, but during my time, used to have a thing called, Seebeck effect and Peltier effect. Karke. If you take two different wires, like copper and some steel or something, and if you send current, one joint becomes hot and one joint becomes cool. You can actually use this for heat, cooling and heating effect. Vice versa, if you take two metals and if you heat them at the joints, you get current in the wire. So there was a concept like that. It's not there in the portion anymore. But why do you think you're getting a charge on the interface? Think about that for some time, 30, 40 seconds, and then I'll explain you why you're getting charged. And then I'll give you a minute to solve. Why will there be potential difference due to resistivities? Battery will create a potential difference. But if there's a potential difference, why do you get charge on a wire? So according to your logic, if you put a resistor, there will be charges here. Listen, the story goes like this. It's a pretty thing. It happens in Mumbai a lot also. Imagine you build a nice, beautiful 4-lane road, right? And then at the end of the road, you make this into a 2-lane. What do you think will happen? What do you think will happen at this junction? You get a traffic jam, right? So if row 1 and row 2, let's say row 1 is made, this is made of copper, the electrons can move freely. So they'll come rushing here and suddenly they'll encounter more resistivity. Then what will happen? Electrons will start getting stuck here. Now, if the electrons start getting stuck here, what will happen? These electrons will repel the electrons which are coming from the left-hand side. So they will slow them down. Vice versa, these electrons will start pushing these electrons to go faster. You're getting it? So this charge will keep on accumulating till, for example, see, let's say this side, say 1,000 electrons are coming, and this side, let's say only 400 electrons can go per second. Example. So every second, how many electrons will accumulate? 600 electrons will accumulate. As the charge starts accumulating, what will happen? These guys will repel so strongly, 1,000 will become 800, 400 will become 600, still electrons will accumulate. This will become like, let's say 700 or something, and this will become 700. You reach a steady state, isn't it? So that charge accumulation is important. That will maintain a new balance, which 700 will come and 700 will go. Inflow is equal to outflow. You're getting it? So this is what will happen. Because both the sides resistivity is different. You're getting this thing? What is happening? Why you're getting a charge there? The electrons are coming from left, right? Once they come there, they get blocked there. Is that clear, everyone? Vihan? So this is a classic example, Mumbai Sea-Link. Ever been on a Sea-Link? I think it is a 4-lane or 5-lane, I guess. It's a pretty large road. So initially when they built it, the purpose was this. Oh, there is so much traffic. If you ever see Mumbai, right? It's like an island kind of thing. And especially this Bandra Mein, right? People have a lot of traffic and all. So they said, oh, let's build a Sea-Link. Then what happened? So people are happy now. They started getting in and going here. As usual, BMC, what they do. So this is a 4-lane. So they connected this to a 2-lane. So the traffic jam which used to happen here now happens here. So what we do is we are simply shifting the traffic up. Now they're building a new coastal road. So we will shift the traffic from here to here. So you don't reduce the traffic. You shift the traffic from one place to another place. Because once you shift the traffic enough to, Borivali side, Vasai, Virar, let them complain, na, who cares? It is not in BMC region anymore. It goes into Thane region. Thane people will handle it. BMC to solve the problem. Now it's TMC ka problem. Now how do we solve this? How do we get the charge? Isn't it? That's how you solve the problem. Throw the problem into someone else. Happens, na? Sister broke the vase. How does he solve the problem? First, she'll go to the mummy running and say, "Mummy, pata hai, brother broke the vase." Whoever complains first wins. Ever tried the tactic? Generally works with younger ones. Elder, the elder one can't do anything. How do we get this? Like I said, this question is easy to solve, but to figure out what the hell to do is a tougher one. So now you need to think about, entire electrostatics. Entire electrostatics. Think about everywhere where charge came. When I saw this question first time, right, long back, even I didn't know how to do, right? So I was thinking, you asked me for charge. Then I started thinking about all the concepts that charge came. So first time charge came in electrostatics. So electrostatics, current, charge, rho. These are the things I have. I, rho, I want charge, electrostatics. Then I started counting. Coulomb's law. No, I can't use. Field. ठीक है, field, but how will I use field? I can't use. Dipole नहीं है. So then gone. Electrostatics over. Then Gauss law. Gauss law में field, charge. Field, charge. Is there any relation? There is one. Flux is equal to Q by epsilon. Capacitors I can't use. So the only thing I got stuck is if I know field, I can use Gauss law. I can find flux. Flux is charged by epsilon. But how do I get field? I know how to get field from current. Because from current I can get J, and J is equal to sigma E. You're getting that? That's how you join the dots. You see what do I have, and you start thinking like, okay, where did I see this first time? And you just keep thinking about every possibility there. You will end up at something and say, okay, this is the only thing that looks possible, and then let me try and see. Now, can you try? I'll give you another 1 minute. That is how I figured out how to solve this. And that is almost 7-8 years back. That happens still with me. If someone gives me completely new question, I have no idea. I sit and I think like that only. What all do I have? What do I need to find? Is there any relation between these two in all the chapters that I studied? I just go back and I just keep searching. Then you start assembling them. This could have happened, this could have happened, and then maybe that could have happened. That is how you learn. That's when you do it is fun. And then when something new comes, you know how your brain is ready to adapt and solve. So there, the idea was clear. Field, flux, charge. There is some relation there. Current density, field area. There is a relation somewhere there. So what we do, we consider a Gaussian surface here. It's imaginary. You can take it wherever you want. So let this side the field be E2. Let this side the field be E1. We know J is equal to sigma E. J is nothing but current by area, and sigma is nothing but 1 by rho into E. So E into area is current into rho. Now in this Gaussian surface, the flux will be E2 is leaving, so E2 into area, E1 is entering, so E1 into area. This must be equal to Q by epsilon. That Q must have been the charge on this. So E2A will be I into rho 2 minus I into rho 1. Therefore, the charge enclosed is I into epsilon rho 2 minus rho 1. Yep, that's it, done. Easy. Like I said, steps are less. If rho 2 is greater than rho 1, like I assume, you'll get a positive charge. If rho 2 is less than rho 1, you'll get a negative charge. If rho 2 is equal to rho 1, it is the same wire. There is no charge accumulation. All clear with this? Any doubts on this? Then combination of capacitors. Same thing what we did in resistors, capacitors. We can do the same thing here. So same thing instead of we'll write all this stuff. There, have a look at this. Exact same definition what we did in series and parallel. If two resistors are in series, that means they have same current and same branch, R1 plus R2, parallel, same potential difference, 1 by R equivalent, 1 by R1, R2. We did in thermal resistance, remember? Exact same story, Wheatstone bridge and extended Wheatstone bridge. So this is a little different one that I showed in capacitors. Capacitors I showed like this, isn't it? This I'm showing horizontal. It still works here. Have a look at this page once. You know all this stuff, So what we have done till now, right? All this J, sigma, and all these are important, kind of neglected ones, but those are important ones. All clear with this stuff? Series, parallel. So what have we learned in capacitors? Everything works. Series, parallel, Wheatstone bridge, nodal analysis, symmetries, right? Kirchhoff's junction law, Kirchhoff's loop law, everything works. Let's see a question. This we did in foundation. We got a cuboid here. This is A. This is B. This is C. This is phase 1, phase 2, phase 3, phase 4, phase 5, and phase 6. So if the battery is connected between 1 and 2, find the resistance. So that is R12 is to R34. If the battery is between 3 and 4, find the resistance. 5 and 6, find the resistance. Get the ratio. So depending on how you connect the battery, you will get different resistances. We have a cylindrical resistance here, radius A. Resistance R. Someone took this thing and they melted it. Like this into a Toblerone. You ever seen a Toblerone? Melted and recast. Like this. So it's an equilateral triangle base. Whose side is it? Find the new resistance. So initially the cylindrical resistance is R. So what is this Toblerone resistance? Finish off. Devan, right? Vihan, you messed up. Get this. Standard Mansell questions. You got a minute. किसी को याद है फाउंडेशन में क्या था ये फाउंडेशन में आई थिंक वी डिड KitKat square cross section right you got a minute C, the first one. I can do like this. Resistance is rho L by area. Multiply length and divide by length. This will become rho L square by volume. So R is proportional to L square. Now be careful with the formula. What is L? L is the length along the current flow. So when you go from 1 to 2, length is A. When you go from 3 to 4, length is C. When you go from 5 to 6, length is B. So don't take any length that you want. When you say rho L by A, L is the length along the current and A is the area perpendicular to the current flow. Got it? Generally, you won't have a problem, but if I ask you the shape, the things get messed up. What about B ka answer? If the cylindrical resistance is R, whose radius is A, you melted this and you made it into a Toblerone thing, equilateral triangle base. Find the new resistance. The lengths are not mentioned. How will you do this? Yeah, it's A square, C square, B square. Most of you got A, B, C, so just be careful. 16 pi square by 3R. Okay, I don't know the answer. Let's see if anyone else got it. 4 pi by root 3. Okay. I don't think so. I think you'll get pi square. Hmm. 1 by pi square. Let's see. Again, same story. What is resistance? Rho L by area. But here area is given. Multiply and divide by area. This will be rho into volume. Length is not given. Then don't bring length into the picture. Area square. The R is proportional to 1 by area square. So resistance R by R nu. What is the area of a equilateral triangle? Root 3 A by 2, half base into height, root 3 A square by 4 ka whole square by pi A square. A square goes off, you will end up with 3 by 16 pi. So our nu is pi A square. 16 pi square by 3R. Got this? So don't try to find length and everything. That is too long. Areas are given, eliminate length, get everything in volume and area, volume and length. So this guy here I eliminated area, here I eliminated length. So you can play like this instead of actually trying to solve length and everything. Medical people do that normally. They find length, area, they do everything. They run out of time. You guys don't do that. Clear? That's a easy question, mains level one. Next one. Any doubts? Just now I had a deja vu. I felt like this happened before. Next one. This is a good one. This we have done before in conduction. We have a conducting shell filled with a medium. So this entire space between them is filled with some medium. Where rho is equal to rho naught x, where x ka value lies between 2a to a. Rho is your resistivity. Rho naught is constant. This inner radius is a, the outer radius is 2a. Do you guys remember where we have done something like this? Heat transfer mein, when we did conduction, we had questions like this. Remember this one? Inner temperature was 2 T naught, outer temperature was T naught. It was the same story. Exact same thing, but yeah, it's now current. And I changed the resistivity here. And then what you did, you are connecting this to the ground. This you're connecting to a battery. I think I'll do reverse weight. Let's say we have a battery here, grounded, V, and the outside is grounded. You're getting how am I connecting? और नहीं तो इतना ground grind नहीं करते हैं. Just keep it simple. Somehow you connected over this. Don't worry how it is done. It is connected. You connected inside and outside. Clear? So they're conducting shells, na? So in and out are connected. The voltage of the battery is V. So current will flow from inside to outside. So remember the blue lines are conducting shells. The green one is a medium, which is rho. First question, find R equivalent. Find current. Find current density as function of X. Find the electric field as function of X. Find heat per second per unit volume. As function of X. Find potential as function of X. We are taking the outermost shell as 0. So this entire inside shell ka potential is V. The entire outmost shell ka potential is 0. So current is flowing radially. There. This is how you can get a pretty good question in advance. This is how they'll ask you. And it has a lot of similarities with the heat transfer conduction. Techniques are same. Get R equivalent. I'll give a minute for that. And then remaining things we can handle. Ln 2/4 pi. लॉन में आया क्या? हो सकता है या लो ln 2/4 पे राइट आना राइट प्रोजा या सही है. Try others. Get the thing. हाँ विहान, you got it. R equivalent तो आना चाहिए. Let's see. So how do we do this thing? So we consider a thin shell inside. All the shells are in series because they have the same current going away. So here the current is flowing radially. So current is flowing like this. So at a distance x, take a thin shell dx. So resistance of this shell is rho, which is rho naught x. Length is dx. Remember, rho L by A. L is the length along the current flow. Length is going along dx by area, 4 pi x square. That is a cross-sectional area. That would be rho naught by 4 pi dx by x. Perfect. So therefore, R equivalent will be, integrate this, rho naught by 4 pi limits A to 2a dx by x. Maybe should I have given rho naught x square or rho naught x cube? Doesn't make sense. ठीक है, चलेगा, big deal. Ln 2. What is current? That is the easy one. V by R equivalent. आ गया current. So that would be 4 pi V by rho naught ln 2. What is current density? J of x, which is current by area. Area is 4 pi x square. I is constant anyway, so current density is proportional to 1 by x square. This can be asked like this as integers. J is proportional to x power n. What is n? Then what is field? We also know J is equal to sigma into E bar. Sigma is nothing but 1 by rho into E. Therefore, E is equal to rho into J, which is rho is again rho naught x. J is I by 4 pi x square. So E will be rho naught. I is constant, which is 4 pi x. So field is proportional to 1 by x. The proportionalities are good, right? Those can be good questions. Mostly a matrix matching. अभी तक हुआ नहीं. Find C and D. Find heat produced per second per unit volume as function of x and find potential as function. D is a good one. If you remember in heat transfer, the question was find temperature as function of x. How will you find heat produced per second per unit volume and potential somewhere in the middle? When x is equal to a, potential was v. When x is equal to 2a, potential is 0. What about in the middle? Try. Heat produced per second per unit volume. Any doubt so far? Anyone didn't get any particular steps here? Look at the word only. It is weird. Matlab, heat per second per volume. So heat per second is I square, which is constant. Resistance, right? So again, which resistance? We are talking about the resistance of the thin cross section, dr, by that small volume, which is 4 pi x square dx. So this is the heat produced in the thin shell. So we have seen how much heat is produced per thin shell per its volume. And what is dr? We have calculated here, rho naught by 4 pi dx by x. I square is constant, rho naught by 4 pi dx by x by 4 pi x square dx. The dx goes off. Yeah, you'll end up with I square rho naught 16 pi square x cube. So this is proportional to 1 by x cube. That's what makes this question good one, proportionalities. The main thing बचा है अभी, potential कैसे निकालेंगे? Find the potential as function of x. Integral EDR. That's not a bad idea actually. कर सकते हैं. That is a good idea. Because you already know the field, right? सही है. I never thought about it. I do it in a different way. Yeah, it looks obvious, but yeah, it never clicked. V. क्या करना था? See how I do. You guys check whether you're getting with E dot DR. आना चाहिए. With E dot DR, you should have got it. Normally, this is how I approach. If you take a thin shell at a distance x, so in this thin shell, the distance is dx and the current flowing is I. So dV is the potential difference across the thin shell, that is I into dr, Ohm's law. So the potential difference across the thin shell is current with a minus sign because potential will drop into dr. So this will be integral dV minus, remember current is constant, and dr will be rho naught by 4 pi dx by x. Limits when x is a, potential was 0. When x is x, you want to find the potential. So v is equal to minus I rho naught by 4 pi ln x by a. No, this was 2a actually. X by 2a. There, potential as function of x will be rho naught I by 4 pi ln 2a by x. X ka value goes from a to 2a. I think if you do e dot dr, you'll get the same. Clear with this? What I did, I took a thin shell, I found the potential difference, and I just integrated it. It's a pretty good one, right? But this is a question, where we combined series, current V is equal to IR, the current density J, E, everything we brought. You didn't see these kind of questions in capacitors. We didn't have anything like this. This thing has more relation to heat transfer, conduction. Man. Clear with this? Let's see one last one for that day. Let's get something which will make you feel happy. Find the resistance. Each segment is a resistance. Next class, we'll be doing this only, all circuits. Whatever we did, we'll do series, parallel, Wheatstone, everything will come again. Symmetries, Kirchhoff's law. So next class will be full of circuits. Each segment is R, find RAB. Get this, you can clearly see there's a symmetry, bisector and axial. Nee, Devansh, that is wrong. Ah. Did you guys realize you can remove the node in the middle? One more minute. We have one answer. Purvaja, right? Let's see. Anyone else? Right, Niharika. One more answer. Nee, Om, that is wrong. Nee, Vihan, wrong. Right, Aditya. We have three answers. See. So this you can clearly see here. You can remove the guy in the middle. So this is a bisector symmetry. So along the bisector line, you can open all the nodes along the line. So these two will join, these two will join, these two will join. It will become like this. Now I can actually fold this, but I can actually get it even faster anyways. So if you see, this entire triangle is R, R, 2R, and this is R, 2R by 3. Agreed? Parallel. This triangle is also 2R by 3. These two is 2R, these two is 2R, 2R, 2R is R, R and the middle one is a resistor. So this whole section is R by 2. So upar jo 3 hai na, these three are in series again. So yeah, you are done. So just redraw the circuit. So we have one resistor, resistor, resistor. Middle we have two resistors only. And bottom will be exactly same, three resistors. So this is 2R by 3. This is R by 2. This is 2R by 3. This is R. This is R. 2R by 3, R by 2, and 2R by 3. Check. If you got this, you are done. So 22R by 35. That is what you should get. If you got the circuit, I think it is done. Then it must have done a calculation mistake. Anyone who didn't get the circuit, ask me. Got what we did, right? So once you open the node, it becomes easy. The top three are in series. Each triangle will add up. Clear? There, that one is the last one for the day. Next class, when we catch up, we'll continue from here. We'll see more circuits. We'll see more deadly ones. It'll be more fun, right? And then after that, next class, we will see resistors and capacitors combination. What happens if we combine both of them? That is a very important and high weightage one. So we will see like that. We will keep on adding up something. Okay, with that, we'll wrap up for the day. So again, we'll catch up on Friday, same time as usual. And do remember, Thursday, there's a test online. So make sure to give it. So, and